Hey there, my name is Brennan, and this is Lab 2 for Projectile Motion. The purpose of this lab was just to, you know, observe an object, a projectile in motion, and then try to model that as closely as possible computationally, both factoring in drag and just using gravity. So as we can see here, this was our experimental results, and then we were able to get honestly pretty great approximations with both of these models, although we'll see where the disparities come in later. Like the first lab, this is really just using Newton's second law of motion and the things that can be derived from that. So we have the velocity update formula and the position update formula. The real difference from lab 1 is that we will actually be using the FNet term here because we will have some amount of force. We won't just have FNet of 0. And so the experiment, we were just throwing this little Among Us plush here, and taking that data, putting in the tracker. Here's what that parabola looked like there. Our initial conditions were just this in motion with no extra force from me being inputted, and our system is the plush. Our surroundings are the earth, which is exerting gravity, and the air, which is creating drag on the plush. So to try and model this using code, basically the same as last week again, except the differences are that we have some actual FNet down here, and then also we can have our drag factor, which you can see is equal to negative b, the coefficient. This is the ball's velocity squared, or the masses, and then it's just a v hat vector. So only difference between these codes are b of 0 versus the experimentally determined b of 0.0032. And we can see that this is what that ends up looking like when we do our no drag situation. So the way these actually stack up, over here the blue was our experimental model. Purple, as one would expect, went higher in the y direction and further in the x direction. Interestingly, when drag was factored in, the best I could get was I was able to get it to end at the same x position, the orange here, but it still went further down in the y and further up in the y. Presumably this is just because my initially determined velocity wasn't quite right that I inputted into the code, because I wasn't I was too imprecise with the data that I was able to collect from just those first two positions and extrapolating from there. Discussion first of all with terminal velocity. We can see velocity without drag is just linear, while velocity with drag has this exponential decay. Eventually this would level out to being flat, and that's what terminal velocity would be when there's no change in velocity. But obviously that's not occurring here. That would happen after more time when the forces have leveled out. Meanwhile, if I threw the plush straight up with the same speed, we would see it take longer to reach the ground, because especially, factoring out drag, which doesn't make much of a difference, the amount of time that it takes to reach the ground is going to be proportional to how much initial velocity it had in the y direction. So since we had some in the x before, if we have that all pointed up y, then it will take longer to reach the top, and then twice as long to fall back down to the bottom. And really, that's all for this week. Thank you, and bye.